Hello everyone, I am Ujjwal and I am excited to share with you the process and results of the predictive machine maintenance which I have chosen for the Altair data science competition conducted by Manipal University, Jaipur. So my journey began with a common problem in manufacturing, machine failures leading to costly downtime and safety risks. My goal was to develop a predictive model using machine learning techniques to accurately forecast these failures. So this is the dashboard of Altair AI Studio. First I imported the dataset of machine predictive maintenance from Kaggle, which consisted of 10,000 data points and initially 14 features, but later on after data pre-processing it consisted of 10 important attributes. These all are the attributes like product ID, type, and air temperature, process parameters, and other mechanical attributes, which is going to play an important role in modeling. So here is the stats view. All these are the attributes. As we can see, there is no missing value, so our data set is perfect for modeling. Now we can also visualize the data set. As we can see, like in our data set, most of the product type is of low grade, then medium grade and high grade. Also we can change the plot type to visualize it differently, like we can change it to pie and donut. So as we can see that here also most of we can see most of them are the low grade, then medium, and then high grade. So we can customize according to our assistance in rapid manner. Actually Altair AI Studio is very user friendly and easy to use for data science and machine learning enthusiasts. Its streamlines are all whole work and which makes things simplified, and it is very good for the person who is not from the engineering background but knows the core concepts of data science and analysis. Now coming to the design preview of modeling, first I drag and drop the machine predictive maintenance dataset here. Then I connected it to select attribute operator, where I selected the important attributes only, since product ID and UDI is not going to play any role in predicting machine failure, so I haven't selected this two. Thereafter I connected this operator to nominal to numerical operator. So as we can see that the type attribute here is not a numerical, so we will change this nominal value to numerical value. Then I have connected this operator to the next operator, that is set role operator. So in where for the attribute failure type I have made the target role as level. Then I connected this set role operator to the split data operator. This operator produces the desired number of subsets of the given example set. In the partition parameter of this operator, as you can see here, I had I 3 ratios 0.6, 0.4, 0.5, and selected sampling type as stratified sampling. I took this sampling because it ensures that the class distribution in the subsets is the same as in the whole example set. If I would have taken other sampling, then it would be majority dominated and the model would have become biased. So reduce the biasness, I selected this. Then I connected set role operator to split data operator. So split data operator has three ports. One port is connected to random forest. I use random forest because it ensemble of decision tree in which each decision tree is trained with a specific random noise, and in my case I trained for whether there is a failure or not and the type and failure type, that is which type of failure. Next, random forest is connected to model simulator, and which is further connected to apply model and to the result port. The next port of split data is connected with the apply model, which is further connected to discretized. I use discretized, in which I set the attribute filter type to single and selected the attribute as failure type. Finally, I connected discretized operator to the performance operator and to the result port. And the third port of split data is connected to model simulator, then to apply model, and finally to the result operator. So once when we run this entire process design, so here we get the performance vector. So as we can see in this confusion matrix or the performance factor that we have only 0.75% classification error. That means our model is 99.25% accurate, which is really very impressive. Also we can see that uh, our this model has predicted 2577 times about failure, in which it has predicted 2571 times that there is no failure and only 6 times wrong, so, making it 99.77% accurate prediction. Similarly with the power failure also, it has only predicted 4 times wrongly, making it 85.19% accurate prediction. And it goes like this. We can see with the tool wear failure, overstrain failure also, and since there was no random failure, so it has not predicted anything. And in the heat dissipation failure, so total number of heat dissipation failure was 32, and out of which it has predicted only 4 times wrongly, making it 84.38% accurate prediction. Similarly, if we see that true no failure and true power failure, all our model has predicted almost 99.88% accurate, 92% accurate, and so on. Now coming to the model simulator, we can see that most likely when the input for the model are set to these parameters like 300 Kelvin for air temperature, 309 Kelvin for process parameter, rotational speed this much, and all this thing. So most likely there won't be any failure, and we would be confident that there will be no failure. And similarly, when this is a parameter set for the ideal condition, then these so this is the important factor for no failure, in which we can see that this target attribute contradicts our model, otherwise every model is supporting it. Also, like, we can change the input for the model. So as we are changing the input for model, so we can see that when we are increasing the rotational speed, so the chances of failure is also increasing. Similarly with the tool wear time, like if the contact of tool and the workpiece is more, so the chances of failure is also increasing. Similarly with the torque also. So we can conclude that, like, this is the ideal condition. If this will be the set for the input parameters, then the chances for failure will be very less, otherwise the chances of failure will be more. Now coming to the random forest model. So these many trees have been created. So if we take randomly any tree, like 4th tree, so we can see that this is the final attribute for which we wanted to predict our model. So if we check for the no failure, so for the no failure, if the target is less than 0.5 and the torque is less than 13.25 Newton meter, then the chance of no failure is almost 100%. Similarly, if we check for the tool wear failure, which will happen only when target is set greater than 13.25, or tool wear time is greater than 188 minute, or the type L is greater than 0.5 and rotational speed is greater than 1471, then only the chances of tool wear failure is more. So this is the random forest model. So that's it. So all these things we have done in the Altair AI Studio. We can also auto model this, in which we can also auto model our data set. So in auto model, the results comes in almost all the machine learning algorithms, and you can check like which is the most suitable machine learning algorithm. So I checked it, and in the auto model also I found out that random forest was the one uh, will give the best performance. Thank you.